Hello Math 99 students, this is the lecture for 9.3 and I'm going to do this in 3 parts. I know on the syllabus it says that it's going to happen in 2 parts, but I broke it into 3 parts because YouTube videos can only be so long, so hopefully this will work. The chapter is exponents and logarithms. And this is some fairly new material, so we're going to have to really bend brain cells around and work on this. Please, please, please do your homework. This is the list of things that's happening in this chapter. Again, I'm going to break these first. It's 9.3. I'm breaking it up into 3 parts for lecture purposes. All right, exponents and logarithms. Now, we've covered this question. You know it's a polynomial function when the exponents are non-negative integers. But in the case of an exponential function, you know it's an exponential when the variable x is the exponent or is in the exponent. So here's the simplest form with no numbers filled in, but b can be any positive number base. Any positive number base. We won't be talking about base 1 because every 1 to the any power is just 1, just draws a straight line, 1 above the origin. But here is, back up a second. Our bases could be between 0 and 1, and it could be greater than 1. So here is the form of the equation that shows the transformations. Again, the last thing that happens to x is the up-down shift. So after we establish what an exponential function looks like, then adding something to the end of the equation is going to shift that function upwards. Adding or subtracting something with x is the horizontal shift, and again, subtraction works, moves it left, and addition moves it right, which is why it's minus h, minus the horizontal shift. A being the leading coefficient is going to vertically stretch this function, just like it does with a quadratic. One more caveat, we will not be discussing exponential functions where the base is negative because we get wild and crazy results and it might be a study of mathematics unto itself, but we're just not going to work with bases that are negative. So let's be careful we understand what the notation is. So what's the difference between negative b raised to the x power, negative b raised to the x power, and negative 1 times b raised to the x power? Well, these two are the same because this is negative 1 times the rest of that piece. Don't forget that b to the x. The exponent has to happen before a multiplier. So that is the case with that one. And then negative 1 is multiplied to that exponential expression. Negative 1 is multiplied to the exponential expression. But in this one, if b starts off being negative, then multiplying by negative 1 means that the base that has that exponent is negative. So we're not going to do this part for this chapter. All right, put these 3 on your calculator and pause the video and then sketch what you see from your calculator. What you should have gotten is a picture that looks like this, and where 2 to the x is the one that sweeps up more or less widely, and then 10 to the x is the one, I'm going to say, hugs the axes most closely. So that's what the increasing base does to the picture. It makes this thing hug the axis a little more. Both y-axis as it's rising off to the left. Now this thing looks like it's got an asymptote, but it doesn't, at least a vertical asymptote. Because I can ask, what's 10 to the third? 10 to the third is huge, it's 1,000, it's way off the edge of my page. And I can go 10 to the 100th, which is be humongous out there in Jupiter. But I can also do down this direction, 10 to the negative first, 10 to the negative second. Let's see. Now, the point common to all of these is going to be 0, 1. That's the coordinate pair of that place. And that is because anything raised to the 0th power is going to be a 1. 2 to the 0th power is equal to 1. 5 to the 0th power is equal to 1. Now if you sketch this and you didn't show them all going through that place, you might want to revise your sketch and show them all going to that place. 10 to the 0th power is equal to 1. If you have forgotten why that's true, you want 10 to the 0th power to be equal to a 0, then let's refresh what happens over here with powers of a number. 2 to the 3rd is 8. 2 to the 2nd is 4th. 2 to the 1st is 2. Now, one of the ways to get down this list is to keep dividing by 2. 8 divided by 2 is 4, divided by 2 is 2. 2 divided by 2 is 1. So the next one down in this pattern is going to be a 1. Here it is over here for 3 as well. And then notice what happens with the exponents. 3 to the 3rd, to the 2nd, to the 1st. So 3, 2, 1. The next power ought to be 3 to the 0th. Can you go negative? Yes, of course you can. So 2 to the negative 2nd is 1 divided by 2, which is the same as 1 over 2 to the 1st. So the definition of a negative exponent is the reciprocal of this number. The reciprocal of 2 is 1/2. Raised to the 1st power. So I really ought to be writing this like that. 1/2 to the 1st. So then 2 to the negative 2nd power is 1 over 4, which is 1 over 2 squared. Like that. So you can have negative exponents. An exponent can be 0, an exponent can be 1. In truth, an exponent can be anything. So when we ask about the domain of an exponential function, all of them are from negative infinity to infinity. But the range, how far down can I go on an untransformed exponential function and still find graph? And the answer is only to 0. And because I'm not gonna, let's see, this thing, I cannot raise a number to a power to get 0. Let's look at that thought. Remember we had large numbers, we got to 1, and then we're getting smaller and smaller and smaller. But is there a power on 2? Can I raise 2 to a power to make 0? And the answer is no. 2 to a very large negative is pretty close to 0. Like 2 to the negative 21st power is more zeros than I have space for. And then a number. So it's very close to the 0, but it's not 0. I can never get to 0. So for the range is from 0, but it's not including 0. But how far up can I go and still find graph? So that's infinity. Now, off to the left of this thing, as I was just saying, as I have more and more negative powers of any of these bases, the number gets closer and closer to 0. For this upper curve, this is a half of a half, which is a half. And a half of that, which is a quarter. And an eighth, and a 16th, and a 32nd, and a 64th. And then if we're talking powers of 10, this is 1/10, 1/100th, 1/1000th. So these curves are approaching this number. And what do we call that? The curve approaches the x-axis, but never touches, so that's an asymptote. The curve approaches but never touches the x-axis, and that we call an asymptote. The x-axis is an asymptote. The equation for that asymptote is y is equal to 0. A lot of data in that slide. Okay, let's talk about transformations. So this is the last thing that happened to x. So what will that make that do, that picture? That picture did go through the point 0,1. It was an asymptote off to the left. And so instead of, let's draw it over here. So instead of going through the point 1 above the origin, this place right here, now it's going to be raised up 3. So, and then the other thing that's true is that the asymptote, which was the x-axis, is now going to be raised up 3. So that is now the low end of the graph. And then that point, this point right here, which is the y-intercept, is also going to be raised up 3. 1, 2, 3. So now this curve looks like that. I should draw that as a nice sweeping, it's kind of an L-shaped. I'm going to put an arrow down that way and sweep up to the sky that way. Now, something that might be helpful is to hold up your hand. This is an exponential function. Your thumb is the asymptote, and this thing shoots to the sky off to the right. Not a very good, I can't spread my thumb apart very well, but that's the picture of an exponential function. Off to the left, it's an asymptote. Off to the right, it shoots up to the sky. This one hit before it was shifted was 1 above the origin. Now it's 4 above the origin. So that place is 0, 4. And this asymptote is y is equal to 3. What happened in that one? Well, this minus 5 is together with the variable in the exponent, so that's a left-right shift, and because it's minus, it went to the right, 5. So my 2 to the x function was this one, and now it's going to go to the right 5. So it's going to go 1, 2, 3, 4, 5 to the right. And this point also goes 5 to the right. 1, 2, 3, 4, 5 to the right. It still has an asymptote at the x-axis, and then it sweeps up off into the sky. This one's a little trickier. What is a negative leading coefficient? That's really a -1 out there in front of the 2. It does not make the base negative because the exponent happens before that multiplier. So that's going to make that thing flip over. So instead of being shaped like this, it's going to be shaped like that. So the original function was 2 raised to the x power like that. This thing is going to flip over. So it's going to be like that. These things take practice in order to learn how to draw. Where does the y-intercept go? Now this one went to 0, -1, and the asymptote is still y is equal to 0. Now, let's talk about domain and range for this one. This one was shifted up 3, remember? So I'm going to sketch it here, up 3, and then it went like, and then it, so that was the asymptote, exponent 1 more. Now, domain for all of these is going to be -infinity to infinity. The range in this one, the lowest it can go is, the lowest it can go is from 3 up to infinity. Infinity gets that, that gets that. Because it will never touch that line y is equal to 3. So the range on that one is that. Okay, on this one, this is a left shift, so the domain and the range are still the same. It just slid over, so it's got the same range, the same low spot, the same high spot. So the domain for this one, the domain for all of them is from -infinity to infinity. The range on this one is going to be from 0 up to infinity, and it will not include 0. This one flipped over, so again the domain is from -infinity to infinity. The range on this one, how far down can you go and still find graph, and that is from -infinity up to 0, but not including 0. Take a minute and just cogitate these ideas, and you might want to pause the camera before I move on. There's my information about domain and range. Okay, just for fun, this is what happens when we do have more kinds of transformations on exponentials. And this is what happens. This is your normal exponential function. This is what happens when the exponent is negative. By the way, we call this an increasing exponential increase. And this one over here, because it falls as you go from left to right, is called exponential decrease. Or the other word we use is decay, exponential decay. And we'll use that in some of our decay problems that we'll be looking at a little bit. These other two functions down here, where this is a leading coefficient that it's negative, you just need to be aware that they exist, but let's not, we won't look at those very much. So this one is the y equals negative 2 to the x. I drew that one previously, that's this one. And then negative 2 to the negative x, when both the leading coefficient and the exponent are negative, you get that picture right there. Kind of a cool picture. Okay. Put both of these on your calculator, and then you'll have us have a look at the graph. So take a minute and put them on your calculator. You might want to pause the video. And here is a picture of those two graphs. Now notice that they're both decay, they're both falling. They keep getting closer and closer to the x-axis as you go out towards positive infinity. But they both draw exactly the same picture. Well, why is that? It's dealing with that definition of an exponent, a negative exponent again. Remember that 2 to the negative first is the same as 1 over 2, all of that to the first power. So 2 to the negative x is going to be the same as 1 over 2 raised to the positive x power. And that's why that one translated. And the negative exponent means that that's true. 1 over 2 raised to the x power. And then that's the same as that. So those two draw the same picture. This is a base that's between 0 and 1. This is a base between 0 and 1. Or you can achieve the same effect by getting a negative exponent. So having a look at these three functions, let's compare them with that exponential function. Let me pull it up again. Where they're all, the bases are a power of 2. And we'll set these side by side. So here is the decay functions, and here is the exponential increase functions. You notice that it draws a mirror image picture on here. And, yep, so these are rising and hugging the x-axis as the base gets larger. These are falling, and they also hug the x-axis as the denominator of the base gets larger. So this is 1/2 raised to the x power, and this one over here is 1/10 raised to the x power. Okay. Closing in on the end here. Try sketching these. I'm going, because for the sake of the length of the video, I'm going to let you try sketching them. This one should be shifted down 5. This one should be shifted left 4. This one, I would sketch the graph as up 6, and then you flip it over the x-axis, so then it's down below. This one got a right shift of 1, up shift of 6. So try sketching these, and then try putting them on your calculator and checking your guesses. And here are some, well, you know, play with these if you like. I'm not as concerned with these with the negative exponents, that you can sketch those. You might try and see if your work is good. Again, put them on your calculator and check your work. On the test, I will definitely have you sketch things that look like this, or like this, or like this. So that one and that one and that one are particularly important to know how to do. Not with a negative base, and not with, or negative leading coefficient, and not with a negative exponent. Well, I have you sketch, but these, if you a little practice, you should be able to sketch those as well.